All right, hello. In this section, we're going to finally be talking about the fundamental theorem of calculus. Obviously, this name is really important. And what the fundamental theorem of calculus is going to do, it's going to unite what we understand about indefinite integrals and what we understand about definite integrals. An indefinite integral is an antiderivative, and a definite integral, it has different interpretations, but the go-to one is that it represents an area, and we are going to see how these things are related. That's what we're going to accomplish with the fundamental theorem of calculus. Now, I said here definite integrals are area, and I put that in quotes. I want you to really understand that definite integrals represent more than just area calculations. Area is our go-to example of something we can do with a definite integral, but I promise there are a lot of deeper things. So let me try to get you to understand that. So suppose I give you this velocity function of a particle. I'm not giving you its position, I'm giving you its velocity. And we want to estimate the net displacement of the particle from time 0 to time 3. And we'll notice that velocity is never negative, so the particle is always moving in the same direction. Displacement and distance are the same, so we can be a little sloppy on this problem. Now, maybe you can think of a way to do this for sure, but we could estimate the distance traveled. We could break this up into, let's do 6 intervals, half a second at a time. So interval number 1 basically goes from time 0 to time 1/2. Number 2 goes from 1/2 to 1. This is not the kind of thing you need to copy if you're watching the video. Just follow along. It's intentionally very tedious. I want you to realize it's something that you could do but don't want to do. So each of these intervals we can think of having a length of time. So the length of time for each one is 1/2. I've intentionally made them all the same. Now we could estimate the speed or distance during each time interval. Not speed, not distance, speed or velocity. In this problem, speed and velocity are the same thing because velocity is never negative. So here it's an estimate. We know that velocity is not constant, but we could take a little snapshot. We could say, all right, over the course of a half second, the velocity probably won't change by all that much. So let's just pick the middle. What's the velocity at time when the clock says 1/4 of a second? And our velocity function just squares things, that's 1/16. So our estimate of the distance traveled, distance is rate times time, so it's going at a rate of 1/16. I don't think I'm bothering with units here, for half a second. So the distance it travels would be 1/32. Right? We can say meters and seconds just for clarity. It goes 1/132nd of a meter, because it's going at roughly a speed of 1/16 of a meter per second for half a second. All right, what about during this next time period? The velocity is now probably a little bit different. Over the course of half a second, it doesn't change that much, but it's changed since the previous half second. We could estimate it by just saying, all right, well, the middle there is 3/4. Square that, we get 9/16. Distance is rate times time, so our estimate of that distance would be 1/2 times 9/16, which is 9/32. And we could keep doing that. I could just decide as a crude estimate of speed, just how fast is it going at the middle of that time period, knowing it's not going to change speed all that much. So this is 25/16, this is 49/16, this one would be 81/16. This one would be 121/16. Multiply each by 1/2. So I have an estimate of how far it goes 1 second at a time. right? It's reasonably accurate. For a half second, it's not going to change speed that much. So I just take a snapshot. How fast is it going at that period? Let's estimate distance, and then do that over and over again. And then I could add all these up. And I'm actually not interested in the number here. I'm interested in the process. Now, hopefully you're noticing that this looks familiar. This looks like a Riemann sum. What we're doing in each one of these calculations is we're taking a value for velocity at some time during that interval, and we're multiplying it by a length of time. And for this example, all those lengths of time are the same. I decided to do it 1/2 second at a time. But here we're doing a value of a function times some sort of interval. Each one of these individually is one distance estimate. And then we're just adding all those together. This is like a Riemann sum. When I walked through Riemann sums before, I called the function f and the variable was x, but it's the same process. Value of a function times some interval, multiply those together, and then add them up for all your different intervals. So if we wanted to make this more accurate, what could we do? We could squeeze the time intervals really, really close. Just a tiny fraction of a second, how far does it go then? Tiny fraction of a second, how far does it go then? That would be more accurate, and we could run a limit. So the limit of this process, right, the limit of Riemann sums gives us a definite integral. So our true distance, the true distance traveled, or technically I should say the displacement, not an estimate, but the true value would be the limit of this process of estimating it. So it would be the definite integral of the velocity function, and the velocity function was t squared. So that's one way of looking at this. If I am starting with a rate, and I'm trying to figure out actually what was the change in the amount, I can do it with a definite integral. But now there's actually a different perspective. We can think, all right, here is our velocity. It's t squared. There was some position function called s of t. And I'm not worried about what this is right now. It's just called s of t. So if we want to know the change in position from time 0 to time 3, we could just say, well, where was this particle at time 3? Where was this particle at time 0? And we'll subtract them. So these two things that I've highlighted in yellow do the same thing, but in different ways. One of them is using the velocity function and doing this complicated thing where we break it up into tiny little intervals and make estimates and multiply stuff together and add all this stuff up with the sigma and then run a limit, right? This is a very complicated way of doing it. This is very simple, but it uses a different function. This is a complicated formula using velocity. This is a simple formula using position. But they're the same. And that's the gist of the fundamental theorem of calculus. So before I even show it to you, the gist of the fundamental theorem of calculus, the complicated definite integral process with a rate, velocity is a rate, is the same as a simple subtraction problem with the original function. That's the gist. All right, so we're going to get there in a second. Let me just mention the calculator can do definite integrals. Depending upon your calculator, it might not know how to do indefinite integrals. Nothing on the AP in the calculator active section would require you to do indefinite integrals. They don't want students with a calculator that does it to have an advantage. But if it's a definite integral, your calculator can do it. Essentially what it does is really, really accurate Riemann sums, and it produces an answer that is close enough to the correct thing. So I'm not going to switch the video. If you're on your a calculator screen on your calculator, go to menu. There's under the calculus menu, you will see one of the options is definite integral or numerical integral. So pull out your calculator and try to do this. And what I will tell you is the calculator just gives an estimate. So for definite integrals on the calculator, or really for anything on the calculator, the calculator gives a very good estimate. But it doesn't understand what the correct answer is supposed to be. So I will just tell you, occasionally you'll do a problem on your calculator, and the calculator gives you an answer like 3.9999834. All the calculator knows how to do is give an answer that's very close to the correct answer. You want to take the leap and say, oh, I bet the answer was supposed to be just 4. But the calculator doesn't realize that. The calculator is just giving an estimate. Right? The calculator is not programmed to round things if it's close to 4. It gives whatever it got. And then you can say, oh, I bet that's supposed to be 4. So this one, for example, if you do it, it's supposed to come out to a whole number, but potentially, and this varies a little bit by some settings and which calculator you have, occasionally you'll get something that's not quite right, but is ridiculously close to a much prettier number. Then you should assume that the calculator has estimated that number but is off a little bit. Okay, so now here we're going to go to the fundamental theorem of calculus, and there are actually 2 of them. I'm not going to give you a detailed proof of either one, but I've already given you an idea behind one of them, and I'll give you an idea behind the other. Detailed proofs for these are really, really complicated, but you have the idea. Remember, here's the idea of the fundamental theorem of calculus. We already saw it. This definite integral involving velocity is the same as this subtraction involving position. So here we go. Fundamental theorem of calculus, part 1. This is the one most people think of when they think of the fundamental theorem of calculus, but there's actually another one. So suppose f is a continuous function on the interval from a to b. So we're assuming it's a reasonably nice function. And let f, like capital F, be any antiderivative. So the idea is capital F prime gives us little f. That's the relationship. So really, even though we're starting with little f, we can think that little f is the rate, and big F is, in some sense, the original function. So part of handling the fundamental theorem of calculus is to say that this function that I've been given, I'm already thinking of it as the derivative of something. So here's what it is. This definite integral involving the rate is the same as this subtraction involving the original problem. Another way I could write this to make it clearer is I could avoid that name little f altogether. The definite integral of a rate is the same as a subtraction involving the original. Now, very often we're going to be computing this and it's hard to keep track of things. We will often use this notation to keep track of this. because we don't want to have to remember so much. There is a very specific way of writing these problems. Do not deviate from how I do it. I will not understand your work. People in the AP will not understand your work. This is not the kind of thing where you write some gibberish on the side and miraculously your answer appears. You want to be very precise. So let me show you how you would do this. So let's do this problem from before. If you did practice on your calculator, you already have things. If you bothered to do this, actually, let's go back and just check this. So 10, 35, what's that, 84, 165. So 286 over 32, something like that. And 286 over 32, right, maybe this is wrong. I don't have my calculator handy as I'm making this video. Let's see, top and bottom are both even, so this is the same as 143 over 16. So this is 9-ish. Right, I think it's 8 and 15/16, assuming I haven't goofed. Now we're going to use the fundamental theorem of calculus to calculate this. So here's the idea. I want to think of this function as the derivative of something. So I need to think of an antiderivative. And I just need one of them. We know there are lots of antiderivatives. Just pick one. So we know our rules here. We would bump this, we bump up the power by 1, but we have to control for that. So this thing right here is an antiderivative of t squared. And then I would write a vertical bar 0, 3. This is why my way of keeping track of what is that antiderivative before I start doing the computations. You don't want to have to remember things. You want this antiderivative to be clearly written down, and then the vertical bar with the numbers on top and bottom in the same order means I evaluate at the top, I evaluate at the bottom, and I subtract them. So this would be 1/3 times 3 cubed minus 1/3 times 0 cubed, and that is 9 minus 0, which is 9. So it turns out that true distance, that true displacement that we approximated before really is 9. Our approximation was quite close. And let me make it clear that it doesn't matter which antiderivative you pick. Suppose you're feeling really difficult, and you decide, oh, Patrick, I want 1/3 t cubed plus 14 to be my antiderivative. It is true that the derivative of this function gives me t squared, so you are allowed to do that. So we would plug in 3, and we would have 1/3 times 3 cubed plus 14 minus what we get if we plug in 0. But what you'll notice here is the 14 minus 14 cancels anyway, and we still get 9. So it doesn't matter which antiderivative you choose. So choose the one that is simplest to deal with. Essentially, if you're thinking plus c, choose the one where c is 0. Just the first antiderivative that occurs to you. So here's an example to try. And let me at least draw the picture for you. Let R, actually try to draw this picture first. And if you feel like you're not getting that right, wait for me to do it. But let R be the region below this graph, above the x-axis, and between the vertical lines x equals -1 and x equals 2, I want you to find the area. So pause first and just draw the picture. So all we need here is a rough schematic to organize the problem. It doesn't have to be all that detailed. We know this is a parabola of some sort, and it has left-right symmetry. So, something like so. Don't overthink it. Here's -1, here's 2. So R is this region. This is just a schematic. I don't need a lot of detail. I just want to understand what's going on. So this whole region is above the x-axis. So the area will be given by a definite integral. Definite integral gives net signed area, but if we're above the x-axis, that's just area. So this would be the definite integral from -1 to 2 of 1 plus 3x squared. By the fundamental theorem of calculus, we think of an antiderivative to that function. So x plus x cubed would work. We plug in 2. If we plug in 2, we get 2 plus 8 minus top minus bottom. Even if they're in quote-unquote the wrong order, top minus bottom. If we plug in -1, we would have -1 plus -1 cubed, which is also -1. So we have 10 minus -2, which is 12. And we could test this for plausibility. This picture is not really to scale, but I'll just point out that here, y is equal to 1. Here, y is equal to 4. Here, y is equal to 13. This is 3 units wide. So I know I haven't really drawn this to scale, but hopefully you find it somewhat plausible that this height, it gets as low as 1, as high as 13. It seems like most of the time it's kind of low and it only gets high at the end. So this sort of suggests that the average height is 4. If the thing is 3 units wide and has an area of 12, then on average its height is 4. And to me, that's believable. I realize this is not a very accurate picture, but it spends a lot of time down here around y equals 4 and only a little bit at the top. It's a more accurate picture that might be easier. All right, I'm just going to tell you there's this thing called the mean value theorem for integrals. It comes up in a later section. I'm going to deal with it in a later section. Once we understand average value, it'll be easier to understand. Okay, now I'm going to try to set you up to understand what's called the second part of the fundamental theorem of calculus. And this is rather abstract, so I'll just tell you it takes most students a couple of attempts to really get this. So pay attention and give it your best shot and ask me questions about it later. So what we're going to do here is we're going to define a function, g of x. It will be defined using a definite integral. So g is defined in terms of a definite integral involving the function f. So the idea is we're starting with some function f and a constant called a. And I'm going to define this function g. So let me give you some sense of what this might look like. So let's suppose here is my graph of f. Actually, I'll do this in a different color. Here's my graph of y equals f of x. And let's suppose here is a. And let's suppose here is x. G of x, using the area analogy, is computing that area. But we want to think of this as a function. The idea is I put x here and got this area. If I put x over here, I would get this additional area and a different value of g of x. So the way you kind of want to think about this is as we're moving forward, we're accumulating area. And g of x is measuring that total accumulation of area. If we go all the way over here, if we move x over to this value, then this stuff counts negative. So we're accumulating area for a while, and then we actually lose area. So that's the idea of G. G is sort of measuring how much net signed area do I have so far. But we think of X as in motion. Right? T here is called a dummy variable. So X is representing the number where we stop the measurement. T is really here just so we can set up this integral. So really this is the T axis in this picture. T starts at A and ends at X. So it's again, this is quite abstract, but the idea is X is representing the specific value where we end. T is not representing anything in particular. T is representing all of these. When a variable doesn't actually stand for anything in particular, we sometimes call it a dummy variable or a formal variable. Formal variables don't represent a number. They're built into just a way of expressing something. So think about, when is G increasing? As I'm moving forward, I'm accumulating area. So G seems to be getting bigger and bigger and bigger and bigger. But then when I go over here, I'm losing area. So G seems to be increasing until I get here and then decreasing. When would G be increasing quickly? Right? You'll notice if X goes from, say, here to here, then in just a little bit of time, I've accumulated a lot of extra area. But if X goes from, say, here to here, then I've accumulated less area. So what we're noticing here is when F is positive, G increases. When F is big, G increases quickly. So I'm not giving you a formal proof, but you might now be able to catch on to, oh, well, there seems to be a relationship here where it's like derivatives. When G is increasing, F is positive. When G is increasing quickly, F is big. It seems like F is kind of like the derivative of G. And that's what this is saying. So if we have this function G defined exactly as I did before, so I'm just repeating that. So if G is a function like this that is essentially defined as an accumulation function, you can think of this as it's measuring how much area has been accumulated underneath F. Then the derivative of that accumulation function is whatever we were integrating. The derivative of this thing, here I'm expressing it without even giving this a name. The derivative of this accumulation function is what we were integrating. So you can think of this as saying that derivatives and integrals cancel. Take the derivative of the definite integral of f and you get f. That's the gist. And that should feel right because integrals are like antiderivatives. So derivatives and antiderivatives are supposed to cancel. It kind of makes sense that derivatives and definite integrals cancel, right? We're starting to realize that definite integrals and indefinite integrals are very closely related. So much so that very often people just say integral, and in context, you know exactly what they mean. But I will say, be very careful using this. This theorem assumes that the lower limit of that integration is a constant and the upper limit is changing. If there are any modifications, you have to use some rules, including the chain rule. So let's just look at an example here. Here, I have inside the parentheses this function that basically is measuring how much area do I get, or how much accumulation do I get when I'm integrating this function. I'm starting at the constant 2 and ending at x. So the derivative from 2 to x the derivative of this accumulation function by the fundamental theorem of calculus is just the thing inside with the wrinkle that the variable should now be called x. So that's just directly from what we saw, part 2 of the fundamental theorem of calculus. Now, what if I'm doing the integral this way, where x measures what's at the bottom? What you could do is you could say, oh, well, I know if the limits of integration are somehow in the wrong order, that's the same as the opposite. And that's like multiplying by -1. Constant multiples do not affect derivatives and integrals. They're just along for the ride. So this would be the opposite of what we got before. Let me write this clearly. So if they're in the wrong order, you have to switch them, and that introduces a negative. Now here, and this is a problem that's going to come up over and over again. It's really tricky. Don't panic if it doesn't quite make sense to you. We want to think that the base function here, I'll call it g. The simple version is when I stop at x. I'm integrating from a constant to x. And we know that g prime of x is sine of x squared. What I'm doing here is I'm taking the derivative, not of g of x, but of g of 4x. The fundamental theorem of calculus in its simplest form is you're starting at a constant and ending at x. Here I'm starting at a constant and ending at 4x. This is now a chain rule problem. My outer function is called g, my inner function is 4x. So by the chain rule, outer derivative is g prime of 4x, inner derivative is 4. G prime of x is sine of x squared. Right, so g prime of u is sine of u squared. G prime of b is sine of b squared. G prime of 4x would be sine of 4x squared times 4. So that's my answer. If you are doing an integral that doesn't end at x, you have to be really careful, and sometimes chain rules involved. We will be circling back to this. This is perhaps the hardest kind of problem that comes up regularly on the AP. Every year there's some rando problem that's really tricky and unusual. This is the one that is hard, but comes up over and over again. All right, we're almost done here. And this is just a question of perspective. Let's go back. First part of the fundamental theorem of calculus can be expressed like this, and I expressed it like this. So this is a version where we're not even thinking about the name little f. We're just saying a definite integral of a rate of change is this subtraction. This principle is sometimes called the net change theorem. And this is not really a separate theorem. It's just a different perspective on the fundamental theorem of calculus. So it says, if we integrate a function's rate of change, so that's what we have over here, and in context, this means a definite integral. If we integrate a function's rate of change on an interval, right? Saying it on an interval implies it's definite. We get the net change in the function's value. This is just measuring how much the function changed. This is the definite integral of the rate of change. So let me show you how you would see this on the AP. So I'm kind of making this up. Let t measure hours since midnight. And this function r of t, and right, intentionally it's kind of awkward. This would be on a calculator active section. They know you have your calculator, so they'll give you functions that are a little bit tricky. Suppose this gives the rate at which snow falls in inches per hour. So let's be really careful. This is a rate. They tell you that very clearly. Read every word. Don't just assume you know what the problem is about. Sometimes the hardest part is just reading, and all the information is there. They are giving you the rate at which snow falls. They tell you at 5 a.m. 2 inches are on the ground. Assuming no snow melts, find the amount of snow on the ground at 8 a.m. This is where you could use the net change theorem. So you could say that the amount of snow at 8 a.m. would be equal to the 2 inches on the ground at 5 a.m. plus the net change. I had 2 inches and then it changed, so that gave me how much I wind up with. And again, this is the net change in amount of snow. So here we're going to use this backwards. A net change in an amount is the same as a definite integral of a rate, and the rate is what they've handed you. So this would be 2 plus the definite integral, in this case from 5 to 8, of that rate of change. A net change in an amount is the same as the definite integral of a rate of change. The definite integral of a rate of change is the same as the net change in the amount. That's the fundamental theorem of calculus, just set up in a way that feels like we're talking about things that are changing. And this can be done on your calculator. You do not want to use the fundamental theorem of calculus. If you learn a little more about integrals and have a lot of patience and cleverness, yes, it's theoretically possible to find an antiderivative. That is not the intended method. When you have your calculator, they are writing problems knowing you have your calculator. Once you understand that this is the computation you want to do, just do it on your calculator. And remember to add 2. So we will be practicing on real AP problems and actually looking at the numbers. I just want you to understand this approach. All right, so there we go. There was a ton going on in this section. I think I talked for about 40 minutes. So a lot to digest. We'll be talking about this in class.